Welcome everybody to the Midterm 1 review. This recording is for everybody who isn't able to attend the normal review in person, or if you just wanted to review some of the things that we go over in that review session, that's fine as well. I'm going to be going over all the exact same things, both in this video and in the in-person review later today. Also, along with this video posted on the Learning Suite, there will be an assignment of practice problems that we're going to be going over today in the review. You should pull that up now because I don't want to have to rewrite all the practice problems on the board. So you should just have that up and should be following along that worksheet as we go through the review as well, and that'll make it much easier. Solutions are also posted if you want to skip around the video a little bit or work on the problems on your own, then look at the solutions. That's totally fine. But I want to first do a brief overview of some of the things we've gone over in class thus far. And after we go through that brief overview, then we'll roll through some of these practice problems that I have. And I should note about the practice problems, they aren't exactly the type of problem that you may see on the exam, but they're here just to test some of the principles that we've learned, and so they should be helpful still in helping to cement some things. So let's just jump right in into the review. So the main things I want to go over are important symbols, important concepts that you guys should know by heart going into the exam if you want to do well. And so let's start just with a couple symbols from set theory. Remember that the universal set is denoted by an S. This universal set, of course, just means, a set with all the numbers in it. And then this universal set can be broken down into subsets with smaller, or subsets, or also known as events. An element of a set is denoted by this symbol, kind of like the euro sign. So a subset or an event of the universal set will be denoted by this symbol. And then a subset will look kind of like that. So a subset, we would use this symbol when describing the relationship between two sets within the universal set. So if we have set A, B, and C, all three of these sets are elements or events of the universal set. And then A could be a subset of B. Or B could be a subset of C, and so on and so forth. Let's see. The empty set is denoted by a 0 with a slash. That just means there's nothing in this particular set. It's a null value. And then finally, if we put a line over a particular defined set, so in this case set B, this means B complement, which means all elements of the universal set that are not B. So if the universal set is 1 through 10 and element B or set B is defined as 1 and 2, B complement would be 3 through 10, all numbers in the universal set that aren't B. Okay, so that's kind of the set theory stuff. Next, I want to talk briefly about combinatorics. So there are kind of two main principles that we want to remember with combinatorics, and then there's going to be an application of one of those principles as well that we want to keep in mind. The first combinatorics rule, what we call the MN rule. This is pretty easy. This is in the scenario that you have two items that you want to find all the ways how to combine them. If you say have 3 shirts and 2 pairs of pants, and you want to know all the combinations of those two, you can just multiply them by each other to find the possible combinations. So in that same example of 3 shirts and 2 pants, I can just go 3 times 2 equals 6. MN rule, M times N. Pretty simple. If we want to know how to permutate all, or in other words, how to order a set, all the ways that you can, put something in order, we do that with a factorial. So if we say have 10 students and we want to know all the ways that we could line up 10 students in a line, that would be denoted by 10 factorial. So 10 times 9 times 8 times 7 times 6, so on. That will give us all the ways to line up those students. So we have the MN rule, how to combine, how many ways can we combine two set values. And we've used factorials now to find how many ways we could permutate a group, or how many ways we could line them up. Now, the critical application of these things is when we get to choosing numbers out of a set. So as opposed to just saying, let's line up 10 students as many times as we can, we're saying, let's find how many times or how many ways we can pick 3 students out of 10. So I just call this blank choose blank, or n choose k, where n and k are integers. So in n choose k, we have n, which is the larger set, the whole group of people, and then k, which is the subset that we want to select out of them. As I said, you could do this with anything. You could have a group of 10 students and see how many ways you can pick out 3 of them. You could have 50 questions on a test and find how many ways you can pick 5 of them. And the way we're going to set this up is we're going to have a fraction where the numerator is n factorial, so the whole set. And then underneath, we're going to have k factorial times n minus k factorial. So if n equals 20 and k equals 10, then this would be 20 factorial over 10 factorial times 20 minus 10 factorial, or 20 factorial over 10 factorial times 10 factorial. And this is going to give us all the possible ways that I could pick a group of 10 out of a set of 20. The reason why this is really useful is when we move on to apply it, we can find the probability, the total probability of an event happening, of us selecting a certain number out of this group. So an example question that you guys had on your homework once was, you had, the question was something like, you've got 20 workers, 5 of them are immigrants, and you have 2 jobs, a dangerous job and a non-dangerous job. Let's say that all 5 immigrants were selected to be on the dangerous job. How probable is it that that could have been random? That it just so happened that all 5 were chosen. And so if we want to find this probability, we're going to apply the MN rule and this n choose k rule in order to find the probability. So we need to do MN, event 1 times event 2, over the total number of possible outcomes, right, that could happen. So in that same example of 20 workers, 5 immigrants, 15 non-immigrants, and 2 jobs, the way we could set this up is we could say, okay, 5 immigrants, choose 5. How many ways could we have 5 immigrants and choose 5 of them to be in this job? And then how many ways are there to pick 5 non-immigrants out of the non-immigrant group of 15? And we're gonna put this over the total number of ways that we could select 10 people out of the group of 20. So we're doing total number of ways that we could choose 5 immigrants, which would be M, times total number of ways we could choose 5 non-immigrants, which would be N, over the total number of possible outcomes that there are. And this will result in a probability. I don't recall actually what this is specifically. Maybe I've got it here in my notes somewhere. Doesn't look like I do. But you guys have done this problem before, so you should have an answer that you can evaluate. And I should mention that this notation right here, 5 over 5 in parentheses without a fraction line, this is simply another way of writing n choose k. This is just a different notation, which is more common in writing than this would be. Excellent. So there is another way you can set these up as well. There are kind of two ways that you can get this outcome. This will work as we'll saying, okay, what's the likelihood that we have 2 jobs that each need 10 people? What's the likelihood that we select 5 immigrants for job 1, which is dangerous, and 0 immigrants for job 2, which is not? And then we would put this over the total number of ways that you could choose 5 people out of a group of 20. So these two equations will give us the exact same probability. It's just 2 different ways of thinking about it, right? Here we're looking at it based off of the 2 jobs that each need 10 people. And here we're thinking about it in terms of the 2 groups of people, the group of immigrants and the group of non-immigrants. And for the denominator, we always need to make sure that this number corresponds to these 2 numbers added up, and that this number corresponds to these 2 numbers added up. So that's a way you can check your work if you're setting these up and you're not sure if you've set it up correctly. 5 plus 15 is 20, 5 plus 5 is 10. 10 plus 10 is 20, 5 plus 0 is 5. Simple way to check your work as you're doing these problems. Okay, let's go ahead and move on a little bit into some more probabilities. All right, so Bayes' rule is going to be pretty important. Bayes' rule gives us the relationship between conditional probabilities and some probabilities that are typically a little bit easier for us to find, which is individual probability of events and intersections. So Bayes' rule states that the probability of A conditional on B is equal to the probability of A intersect B over the probability of B. We can rearrange this. Say we know the value for A conditional on B and the value of the probability of B, but we don't know what this intersection is. We can rearrange this to be probability of B times the probability of A conditional on B is equal to, is equal to the probability of A intersect B. And you can see algebraically how these 2 formulations of Bayes' rule are the same. This is going to be pretty important. I would definitely memorize this. And additionally, an important check that we're going to use a lot will be the check for independence. And when we check for independence, we say that if two events are independent, then the probability of their intersection should be equal to their probabilities multiplied by each other. When we look at Bayes' rule and conditional probabilities, what we're saying with independence is that B should not affect the likelihood of A, right? The probability of A. Therefore, the check for independence for conditional probabilities is the probability of A conditional on B should just be equal to the probability of A, right? B has no effect on A, therefore, if we know that B has happened, it shouldn't affect our thoughts on how probable A is. All right. Next up, I should mention as well real quickly, I think that with a lot of these, it can be very useful to draw out diagrams. And for those who have been in the lab, you've probably seen me draw out a lot of these, but especially when they ask you questions like asking you to say, find the probability of A conditional on A intersect B, and you have to apply Bayes' rule and say, okay, probability of A intersect B over the probability of A intersect B. This can look pretty daunting if you don't have any way to visualize it. But once you set up a system to visualize things like this Venn diagram, then it becomes much easier. If you look at, okay, where's A intersect B on this diagram, it's clearly this spot right here, right? The center of the Venn diagram. Then if you ask yourself, okay, where's A? Well, it's just this circle here. And so where does A intersect B? Well, it's just this area. It's just the intersection of the two, right? Because this is A intersect B, this is the only place where they overlap at all. So what looks fairly daunting at first then just simplifies to the probability of A intersect B over the probability of A intersect B, which is of course 1. So it can simplify pretty quickly, and it becomes pretty intuitive and pretty easy once you have a way to visualize. So I would definitely recommend drawing anything out if you have trouble visualizing things. All right. Now let's go over a couple symbols to keep in mind. We're going to be moving now into expected values and variance. So the expected value of x is simply the sum of all x values, it's essentially the average. So we could write this out in two ways. We could say the sum of all x's multiplied by 1 over x, or not 1 over x, sorry, 1 over n, the number of x terms that there are. Or if we're looking at x's that have associated probabilities with them, then we're going to do the sum of all x's multiplied by their probabilities. And this is essentially the exact same thing as 1 over n sum of xi. It's going to give us an average. This, though, is a weighted average based off their probability, and this is just an unweighted average. Okay, so that's the expected value of x, is it's essentially just a weighted average of x. And we also denote it as mu x. Mu x is the sample mean, or rather the population mean. So if you should think of these as interchangeable symbols. They mean and represent the exact same thing. And if you need to write out any proofs, this is a useful thing to keep in mind. Any e of x you can substitute with a mu of x, and that normally helps us to simplify things quite a bit. The variance of x is equal to the expected value of x squared minus mu of x squared. Variance is simply a way of us showing how much individual x's vary from the mean. We square it not really for any particular mathematical reason, but rather just to make the differences even greater in order to make analysis easier. V of x, or the variance of x, is also denoted by sigma squared of x. And then the standard deviation is denoted by sigma of x. So the variance of x, the square root of the variance of x, is equal to the standard deviation, which is sigma. So I would make sure that all of these symbols are etched into your brain, and that you can just kind of switch between them as needed. You know, you can write variance either as this or as that, expected value as this or as that, standard deviation as this or as that. And that will help you to simplify proofs, as typically switching from these symbols into the mu of x or the sigma squared of x or sigma of x will help you to simplify those proofs and see clearly why they're true. We're not going to go over any of those proofs right now, but you've had to do all of them in your homework, so feel free to go over those. Now, let's go over a couple algebra shortcuts real quick. These will be very important. If you have the expected value of a constant plus a coefficient times x, we can pull out this constant a and add it to b times the expected value of x. So since these two terms aren't changing at all, since they're constants, their averages will just be themselves, right? If a is 2 and we add up 2 10 times and then divide it by 10, it's just going to be 2. So we can pull those things out in order to isolate the e of x. So this is very important. Likewise with variance, if we have the same type idea of variance of a plus bx, we can also simplify this quite a bit. A isn't varying at all, right? Nor does it directly impact our x values. And so we can just get rid of a. It goes to 0 when we pull it out. When we pull the b out, we need to square it, since variance is a squared function by definition. We have to square that when we pull it out. And we'll go over this slightly later, but we then add a covariance term. Covariance, though, of a single variable is 0. And so if we just have this setup of variance a plus bx, this term also goes to 0, and we're left with just this. So we'll go over covariance in just a second longer, but these are very important algebra shortcuts to know how to pull things out of expected value and variance functions. All right, I want to get moving slightly faster here. Okay, so covariance real quickly. So if we say have the variance of x plus y. We can use algebraic shortcuts here as well. In fact, I'm going to change this example slightly to be variance of 2x plus 3y. So we're going to need here variance terms for both x and y, and then a covariance term. So we can use the same algebra shortcut as before and pull this 2 in front of the variance of x, but we need to square it, as we had previously stated. We can then do the same thing with y, pull the 3 out and square it, multiply it by the variance of y. And then this is going to be multiplied by 2 times these two coefficients times the covariance of x and y. So this would simplify to 4vx plus 9vy plus, what's this, 12 covariance xy. And this would be the most simple form that we could get this in unless we had values for the variances and the covariance. But this would be a simplified term and is directly equivalent to this equation as well. All right. Let's talk about correlation real quick. Correlation of x and y is also denoted by the Greek symbol rho, the P looking thing. You'll often see it rho xy. And the correlation is equal to, correlation of x and y is equal to their covariance over the standard deviation of x times the standard deviation of y. Covariance of x and y is also denoted by the symbol sigma xy. And so this same equation can also be written sigma xy over sigma x times sigma y. Cool. All right. So let's quickly talk about joint distributions. They'll be important going forward. So a joint distribution will look something like this. The probability of x, y equals, and then we'll have a big function. We'll say have like, here I've got some numbers here. It'll look something like 0.2 if 2010, 0.1 if 2015, 0.1 if 3010, so on and so forth. And these probabilities here will all add up to 1, and they will cover all of the intersection points of x and y. To this point, we've only talked about discrete numbers, so whole numbers, and that's how it'll be on the test. Going forward, we'll talk a little bit more about how to deal with continuous numbers. But in this case, we have very defined intersection points of x and y and all the probabilities. So this same thing up here, 0.2 if x is 20 and y is 10, this could be rewritten as the probability of x equals 20 intercept y equals 10 is equal to 0.2. That is equivalent. And so you should be prepared to write things out in this notation of all the probabilities listed within these brackets and then the corresponding intersection. Each joint distribution also has marginal distributions that accompany it. And the marginal distribution is pretty simply just the likelihood of these individual variables happening. So this would look something like probability of y is equal to, if we were to be going off of this, we could say probability of y if 10 would be 0.3. And then let's just say, I know I didn't write out the rest of these numbers, but let's just say that for the rest of these numbers, y equaled 15. Then we would say 0.7 if y equals 15. So these should again sum to 1, and they represent all of the possible values that an individual variable within these joint distributions can take on. Okay. I haven't gone over everything that we've talked about, but I think that's going to more or less conclude this going over of materials. Now we're going to go ahead and look at some of those practice problems that I have provided you. So again, pull up the sheet on the website or on the Learning Suite, and go ahead and follow along as I go through these. So first off, we have a set of true and false questions. These are going to be, you're going to see true and false questions on the exam, as Professor Jensen has told you guys. So the first example that we have is if A and B are mutually exclusive, then probability of C is equal to the probability of, and right now I think I need to correct this sheet slightly, but probability of C conditional on B, C conditional on A plus the probability of C conditional on B. So what this is saying is that the probability of C should be equal to the probability of C conditional on A, or in other words, the probability of C happening if A happens, or the probability of C or the probability of C conditional on B, so probability of C if B happens. This statement is false because we don't know if A, B, and C are collectively exhaustive in the universal set. If that was the case, if A, B, and C were collectively exhaustive and mutually exclusive, and A and B are mutually exclusive, then this would be true. But since we don't have enough information on that, we can't say whether or not it's true. Okay, the second one, if X and Y are random variables with a correlation of XY correlation X2, yeah, I need to edit this sheet. It's kind of formatted weird. But it essentially says if X and Y are random variables, then the correlation of XY is equal to 2X. The correlation of 2XY is equal to 2XY. And the original correlation untransformed is X times Y. So let's build this out. Correlation is equal to the covariance of X and Y over the standard deviation of X times the standard deviation of Y. We have adjusted 2X, or we've adjusted X rather to be 2X, so we can rewrite this as the covariance of 2X and Y over, I'm going to write these out as variances, over the square root of the variance of 2X times the square root of the variance of Y. So we can pull out this 2X, or rather just this 2. So this becomes 2 covariance XY. We can also pull this 2 out of the variance here. When we pull it out of the variance, we have to square it, right? So it becomes 4, but then we can pull it out of the square root symbol by taking the root of it, and it just becomes 2 times variance of x times variance of y. These 2's will cancel out and just become 1, and we're left with covariance xy over square root of the variance of x times square root of the variance of y. This is equal to this original equation. The correlation of x and y just becomes xy. So this question is false. Okay. Next up, we've got something that we kind of went over a little bit. Variance of 3x minus 5y. And it says that this is equal to 9vx plus 25vy minus 30 covariance xy. And so we have to prove or say whether these two things are equal. Well, using the algebra shortcuts that we talked about earlier, we know that we need a variance term for x, a variance term for y, and a covariance term of the two. So that looks pretty good so far. For the variance term of x, we can pull out the 3 and square it, which of course becomes 9 variance of x. So that checks out. For the variance term of y, we can pull out this negative 5 and square it, which becomes a positive 25. So that checks out. And then for the covariance term, we know that it needs to be 2 times these two coefficients. So 3 and negative 5 times the covariance of x and y. 2 times 3, 6 times negative y is negative 30, or negative 5, not negative y. So this results in 9 variance of x plus 25 variance of y minus 30 covariance of xy, which is this, and thus the original statement was true. All right. Last on the true-false, says to find the joint probability function of two random variables, multiply the marginal distribution functions together. So this this question more than anything is just, do you know kind of your definitions of what a marginal distribution function is and what a joint distribution is. So we talked about how the marginal distributions are the likelihoods of x and y, or however many variables there are happening. So if say x can be 0 or 1, then its marginal probability could look like 0.6 if 0, 0.4 if 1, something like that. So this question is positing that if we multiply the two marginal probabilities together, that we'll end up with their joint probabilities, or all the intersections. This is only true though if the two variables are independent. We know this because the joint distribution function, or probability xy, is equal to all of the intersection points. So probability of x equals 1 intersect y equals 0, probability of x equals 2 intersect y equals 0, so on and so forth. And we know that the probability of the intersection of two variables is only equal to the probabilities multiplied if they're independent. This is our check for independence, right? And so this statement can only be true if x and y are independent of one another, and thus the answer to this question would be false. It's not always true. It could be false if they're not independent. All right. Now we're going to get into some of the long answer questions. So give me just a second to pull this up so that it doesn't take me forever to go through this. All right. This is kind of hard to see on the document that I gave you guys because they can't format these joint probabilities super well. But it says X, Y, and Z are Bernoulli random variables. I'm not sure if we ever used the phrase Bernoulli in class, but it means binary, essentially. It can be 1 or 0. Bernoulli random variables. So we get probability X, Y, Z is equal to a big old joint distribution function, 0.2, 0.1, 0.1, or sorry, that one's 0, 0.1, 0.1, 0, 0.2, 0.3, and sorry, I should have written this up beforehand. If X, Y, Z equals 0, 0, 0, I'm gonna omit writing if X, Y, Z for the rest of these, just to make it a little easier on myself. Almost there. All right. So it gives us this joint distribution, and then it asks us to find first the marginal distribution of y, or sorry, not of y, of z. So probability of z. We know z can only take on 2 values, 0 and 1. So we can, or sorry, I'm going to say if 0, if 1. And now in order to find this, we simply have to find the sums of all the probabilities where z equals 0 and 1, right? So z is our third variable here. All the zeros, z equals 0 here, equals 0 there, equals 0 there, equals 0 there. So we say, all right, 0.3, 0, there's a 0% chance of this happening, and 0.2. So 0.3 plus 0.2, 0.5. And then if 1, well, z equals 1 there, 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 and there. 0.3 plus 0 plus 0.1 plus 0.1 also equals 0.5. This is perfect because these also add up to 1, telling us that we did it right. And that's all you got to do for something like that. Just add up those probabilities. So now, part B asks us to find the joint distribution of x and y conditional on z being equal to 1. So we need probability of xy conditional on z equals 1. Okay, so there are going to be 4 possibilities. Four possible outcomes. 0, 0, 0, 1, 1, 0, 1, 1. Those are all the possible outcomes. And we essentially need to find probability of x intercept y intersect 1 over probability of z equals 1, right? Okay, so for this, we can kind of do a similar process as we did on the last one. We can say, okay, where are all the ones where x and y equals 0? Well, that's true here, it's true there, and it's not true anywhere else. So these are our two options, but z only equals 1 for one of these, right? Here it equals 0. So this is eliminated, and we end up with the probability of the intersection of x and y and z equals 1 as 0.1, and then we have to put that over the probability of z being equal to 1, which we found in the previous marginal distribution function for z, that's equal to 0.5, and thus this first one is 0.2. Next, we can go through the same process. Where is x 0 and y 1, where z is equal to 1? So x is 0 and y is 1 here, though z is equal to 0. It's true here as well. And for none of the rest of them, we can eliminate the first because z is not equal to 1 at that point. And we again get 0.1 over 0.5, which again equals 0.2. For the next one, where does x equal 1 and y equals 0? Let's see, that's true here and that's true here. Z, however, is only equal to 1 on this one. We look at it and there's a 0% chance of this happening. And so this just becomes 0. 0 over 0.5 equals 0. Lastly, we have 1, 1, which are true at these 2 points. Z, however, is only equal to 1 here, so we can get rid of this. And we get 0.3 over 0.5, which equals 0.6. 0.2 plus 0.2 plus 0.6 equals 1, so we did it correctly. And I hope you're starting to see now how we can use this joint distribution function to find conditional and marginal probabilities by a really simple process of just kind of identifying and adding things up. All right, now things start getting slightly more complicated. We have to find the correlation coefficient between x and y conditional on z being equal to 1. So this, I'm going to explain 2 ways how to do this. The shortcut way using knowledge about the Bernoulli distribution, and then I'm going to explain how to do it the long way, but I'm not going to do it the long way. So we're looking for the correlation coefficient of x and y conditional on z equals 1. So we know that we need the covariance of x and y conditional on z being equal to 1 over the standard deviation of x times the standard deviation of y. So a fun thing about the Bernoulli distribution is that since the only possible outcomes are 0 and 1, if we do our normal expected value of x, for example, typically what we would do here is we would multiply the value of x times the probability of it happening. So for the first value, we would say, okay, the value of x is 0, the probability is 0.2. And then we would add that to the next value, x is equal to 0, probability is 0.1, so on and so forth, right? Well, you can see how both of these terms are just going to be 0. All of the terms, in fact, where x equals 0 will just be 0. So the first 4 values all just become 0. And then after that, the only other value for x is 1. So we would end up with 0.1 times 1 plus This is another 0 value because the probability is 0, plus 0.2 times 1 plus 0.3 times 1. This, of course, just becomes 0.1 plus 0.2 plus 0.3, which equals 0.6. So the expected value of x would be 6, or would be 0.6. And the thing I want to point out with this is that this value of 0.6 is equivalent to the probability that x equals 1. So with Bernoulli, the expected value of a variable will just be equal to the probability of that variable equaling 1. Because if it doesn't equal 1, it equals 0, and thus the value of that term becomes 0. Therefore, this is true. So the expected value of x here is 0.6. The expected value of y, if you add up all those probabilities over there, becomes 0.8. And these aren't conditional on z being equal to 1, they're just in general. Now, to find the variance and then the standard deviation of these numbers, which we need for the denominator, typically we would do e of x squared minus mu of x squared. We've got mu of x right here, and then we would just have to do the same process over again to find e of x squared, just squaring all of our terms. So we would go 0 squared times 0.2 plus 0 squared times 0.1 plus 0 squared times 0 plus 0 squared plus 0.1. Kind of a tedious process. There's another shortcut with Bernoulli variables where the variance of again, this is only for Bernoulli distributions where they're binary. The only options are 0 or 1. The variance of the Bernoulli is just equal to the probability that x equals 1 times the probability that x equals 0. So in this case, the probability that x equals 1 is 0.6. We can multiply that by 0.4, which is the probability that it equals 0, and we find that the variance of x is equal to 0.24. Again, if you wanted to solve this a more traditional way, you totally could. I just don't want to do it because it'll take a while. But if we wanted to do this the normal way, we would do 0.2 times 0 squared plus 0.1 times 0 squared plus 0 times 0 squared. So on and so forth. We would go down all of these values, and then we would subtract from that 0.6 squared, which is the mu of x, which is also just 0.36. And you'll end up with the exact same variance, which is 0.24. Variance of y, then we can use the same trick and do 0.8 times 0.2, which I don't know why I can't do math right now in my head, but geez, why can't I do math in my head right now? 0.8 times 0.2. It's not just 0.16. It is 0.16. What am I going on about? Okay. It's 0.16. And then to find the standard deviations of these, we just have to take the square roots of these two values. We end up with sigma x is equal to 0.49, and sigma y is equal to 0.4. So in our equation up here, we can now put covariance of xy conditional on c equals 1 is equal to 0.49 times 0.4. Perfect. We're getting there, as they say. So now the covariance of x and y, let's see, can you guys see this? Okay, covariance of x and y is equal to the expected value of x times y minus minus the mean of x times the mean of y. So we've already found the two means, 0.6 and 0.8, so we can sub those in. Now we just need the expected value of x and y. So the expected value of x and y, and this is specifically conditional on z being equal to 1, so we're going to use this table. And all we do for this is we do the probability times the z value, or times the x value, times the y value. And then we add that to probability times the next probability times the x value times the y value, plus the next probability times the x and the y values, plus finally last probability times the x and the y value. As you can see, these three terms are all going to be 0, and then the last term will be equal to 0.6. So 0.6 is the covariance, or rather is the expected value of x and y, so we can plug that in right here, minus the means multiplied, which is 0.48. We end up with 0.12. Excellent. So we can plug that in right here to get 0.12. Sorry that this is getting rather messy. 0.12 over 0.49 times 0.4. And that is equal to 0.612. I know that's a lot of work. I can guarantee you that you'll have to calculate a correlation coefficient at least once on the test. So I definitely understand how to find covariance, expected value of xy minus mu of x times mu of y, and how to get to these standard deviations. Notice that these standard deviations are not based off of the same conditional probability as the covariance. These are just the standard deviations of x and y, conditional on nothing. Whereas this covariance on the top is what's being affected by this conditional value of z being equal to 1. Okay. Again, I know that was kind of long, but good processes to know. All right, we've got one more example to get through. I'm sorry that this video is so long. I hope it's helpful in some way. And if not, at very least, you've got these practice problems and their answers to go over. All right, let me pull up this other one real quick. Where is it at? Okay. Okay. So, this question asks, suppose I buy a mystery bag of Lego minifigures for my daughter. Note, I did not write these questions. I do not have a daughter. The bag contains 5 minifigures randomly selected from the major characters in Ninjago. Suppose that the pool of major characters includes 5 good guys and 9 bad guys. Within a bag, no minifigures are duplicates. What is the probability of getting 3 or more good guys in the bag? Okay. So, in order to do this, there are a couple of ways that you can organize yourself just to keep things consistent with the rest of the class. We're going to write out a distribution of all possible outcomes. So we're trying to find the probability of getting 3 or more good guys into a bag. For this, we're going to use n choose k to find these probabilities. So this might be a bit of a grind, but we know that there are, okay, let's just, to organize ourselves, say this value will be for y, or good guys, equals 0, y equals 1, y equals 2, y equals 3, y equals 4, y equals 5. And we're trying to find the probability that there are 3 or more good guys in the bag. So for this, using our n choose k setup, we're going to say, okay, how many ways can I pick 0 good guys out of the possible 5? And then, let's see, how many are in the bag? 5 are in the bag. So then we would choose 5 bad guys of the 9, and that would be over the total number of ways that we could select 5 out of the 14. So this is going to give us the probability of us pulling 0 good guys. For the next one, we just do pretty much the same process, just how many ways can we choose 1, and then how many ways can we choose 4 of the bad guys over the total number of ways that we can pick. Oh, that should not be a division sign. Okay, on the next one, same thing, 5 over 2. How many ways can I pick 2 out of the 5? And then how many ways can I pick 3 of the 9 bad guys over, again, 14 over 5. This is going to get real cramped real fast. I'm going to move these down. So then, how many ways can I choose 3 out of the 5 good guys and 2 of the 9 bad guys, or 14 over 5? How many ways can I choose 4 good guys and just 1 of the bad guys, over 14 over 5? And then finally, how many ways can I choose all 5 good guys, none of the bad guys, over total number of ways to select 5 out of 14? So just for illustrative purposes, the way we evaluate this is this first one would be 5 factorial over 0 factorial times 5 factorial. That would be multiplied by 9 factorial over 5 factorial times 4 factorial. And then that whole thing would be divided by 14 factorial over 5 factorial times 9 factorial. I'm not going to crank all of those numbers right now, but if you do crank the numbers, this equals 0.0629. So you would go through and crank the numbers on all of these. If you want to do that, you can pause the video right now. I would encourage you to practice this and go through and do them. But you end up with the following probabilities. All right. But we're not quite done, because the question asked us what's the probability of getting 3 or more good guys. So then we just need to add up these probabilities of 3 and greater. And this results in 0.2028. This is the probability of getting 3 or more good guys. All right, so then question B, if good guy minifigures are worth $2 each and bad guy minifigures are worth $1.50 each, what is the average value of each bag? What's the standard deviation? Okay, so first off, we need to know the expected value of, or rather the expected value of Y, or how many Ys are we gonna get in a bag? And by Ys, I mean good guys. So the expected value of Y is equal to the sum of all Ys multiplied by their probability, right? So we're going to have 0 times its probability plus 1 times its probability plus 2 times its probability plus 3 times its probability plus 4 times its probability plus 5 times its probability. All right. If you evaluate all of that, you end up with 1.7858. So then to find the value of the bag, we know good guys are worth $2. So we'll do $2 times the expected value of good guys. Bad guys are worth $1.50. And we know that there are 5 people total in the bag, right? And so we don't need to find the expected value of bad guys. We can just subtract them, or we can just subtract the expected value of good guys from the total number of figures in the bag, which is 5. And then we can multiply that number. That number will give us the average number of bad guys in the bag. We can multiply that by 1.5 to find their value. If you evaluate that, it may or may not, oh yeah, here it is. If you evaluate that, you end up with $8.39 is the average value of the bag. And then we need to find the standard deviation of bag values. In order to do that, this gets slightly more complicated, but we're going to call this, we're going to say value of a bag is equal to the variable V. So we're looking for, first, the expected value of V. This is the expected value of the bag, is what we just found, $8.39. In order to find the standard deviation of the value, we now need to find the variance of V, which of course is equal to the expected value of V squared minus mu of V squared. So this now gets slightly complicated. V is equal to $2 times Y, the number of good guys, plus 1.5 times X, the number of bad guys. So in order to find this expected value of the two, we have to roll through all of the potential values for those numbers. So we would first do the probability 0.0629 of Y equaling 0. If Y equals 0, X equals 5, right? So we would say $2 times Y equals 0 plus $1.5 times X equals 5. And since we're looking for the variance, we have to square this 0 and this 5. We would add to this term the next one, probability 0.3147, multiplied by $2 times the number of good guys, which is 1, number of good guys squared, plus 1.5 times the number of bad guys squared, which is 4 squared. We would add to that the next probability, 0.4197, times 2 times the expected value of good guys squared, plus 1.5 times the expected number of bad guys squared, so on and so forth, down through to 5. That number ends up being about 70.6395. So I know that this is kind of convoluted and difficult, but it's kind of the same process that we've always been doing, right? Where we're simply plugging in the different possible values, multiplying them by their probabilities, and summing them. So now if we come back over here, we have 70.6395 minus 8.39 squared. And the final value we get here is for the variance is 0.1987. Very low variance in values of bags. But we're not done yet, because the standard deviation is of course equal to the square root of the variance. Thus, we have to take the square root of this number, take the square root of 0.1987, and you end up with 0.4485. All right. Let's see. The other way you can do this, which is simpler, is you can find the variance of the number of good guys in a bag, and then use that variance in order to find the standard deviation. That process is slightly less intuitive though, but definitely possible. All right, finally, part C. Suppose that my daughter especially wants a minifigure of the good guy ice ninja Zane. What are my chances of getting at least one Zane if I buy 3 bags? All right. I'm going to get rid of some of this stuff. Okay, so the probability of getting a Zane is equal to, we're gonna again use the same process. 1 choose 1, there's only 1 Zane, we need to pick Zane. And then there are 13 other characters that we can choose from. We need to find all the ways that we could choose 4 of them, since we've got 5 people total in a bag. And this will be over 14 over 5. If you evaluate this, you find that there's actually a pretty decent chance of pulling a Zane, just over a third. And then if we, there was a question kind of like this in one of the homeworks where it asked about 3 students being able to solve a math problem. And it asked what's the likelihood of at least one of them getting it right. So there are a ton of combinations, permutations of one person getting it right. Student A could get it right and the other 2 could get it wrong. Student B could get it right, the other 2 could get it wrong. 2 of them, A and B could get it right, but C could get it wrong. C and A could get it right, but B could get it wrong. So there are tons of possibilities, and we could find the probability of all of those possibilities happening and then sum them all together, but that would kind of take forever. The easier way to do it is to find the probability that none of them get it and then subtract that from 1, since that's the only case when it doesn't happen. In this case, if we're buying 3 bags, we could find the probability of bag A or bag B or bag C having the Zane in it and calculate all of those possibilities of getting at least a Zane, 1 Zane in one of them. But the easier way to do it is to find what the probability is of getting no Zanes in any of them. So we found that the probability of getting a Zane is 0.3571. Thus, the probability of not getting a Zane in a bag is equal to 1 minus that. And if we multiply this probability by itself 3 times, this gives us the probability of us having 3 bags and none of them contain Zane, right? Since these are independent events. We then just have to take this whole thing and subtract it from 1 representing all possible outcomes in the scenario. And that results in 0.7343. This is the odds of pulling at least 1 Zane out of 3 bags is about 73%. All right, those are the practice problems. I know this was a very, very long video. I hope that it was helpful in some way. If you have any questions, please come chat with me in my office hours. I'd love to help you guys. You guys are going to do well on the test. It's definitely something that I know there are kind of a lot of topics to go over, but if you kind of commit a couple of important details to memory, you can do very well on the test. So I wish you all the best of luck. Again, come talk to me if you have any questions. And